make its noise. It is recording now. This is a legacy problem in that it's very useful when we're meeting in person and not as useful otherwise. It is an example of damped harmonic motion. So practice for damped harmonic. Okay, let me share the problem on the screen here. Oh, I always forget it opens that. Alright, what we have is a pendulum with a length of 1 meter, and it is released from an angle of 15 degrees, which, while not normally considered small angle, we'll treat it as though it is here. Okay. Let's see, what else do we know? After 1,000 seconds have elapsed, the angle has reduced from 15 degrees down to a maximum of 5.50 degrees. Okay. And then we're asked to find what is the value of the damping coefficient, well, not the damping coefficient on its own b, but b over 2m, which is essentially the time constant for it to fall by, I think it's 60% or so. Okay, so let's come back to my screen here. Alright, this may be a pendulum, but it still follows broadly the same rules as a mass on a spring would. So we've got the original amplitude, we've got the damping term, which determines how much it falls off, or how quickly it falls off, and then we'll have a cosine omega t plus phase term, where this time the omega is some much more complicated expression, something like g over L minus, I think it would be something like b over 4m, or b over 2m squared maybe? I don't know. The truth is we don't need this part, so I could go and look it up on the formula sheet if I need it, but we're not going to need it here. Now the question is, well, why the heck not? Okay, well, let's talk about that. We have an angle theta, we have a t, and it starts out at its maximum and it will fall off, and then it will proceed to oscillate, decreasing in magnitude continuously from thereafter. And we know that this starts out at, this starts out at 15 degrees, and at some point you get 5.5 degrees at some time 1,000 seconds later. Now here's the thing, if we know that it's 5.5 at its largest, that means we're looking at 2 points that are at the peak. Let's say this is 0 for the sake of argument. It'll make this a little bit easier to understand. So that means theta as a function of time will look something like our theta naught, which is our 15 degrees, e to the minus b over 2m cosine of omega t. Well, if t is equal to 0, then cosine omega t is equal to 1. And if we're looking at a max at 1,000 seconds, that means cosine of omega times the 1,000 seconds, it's also got to be at its maximum. Otherwise we couldn't compare the two and say how much it's fallen off. So that's actually the trick we need to find our answer. Theta at 1,000 seconds is going to be equal to 5.5 degrees, which is equal to 15 degrees e to the minus b over 2m times our 1,000 seconds. Now, I don't have to put all these values in here. As a matter of fact, it's better to handle this in variable form, so I'm going to rewrite it in a variable form here, so we can solve it in pure variables. Alright, so if I want to find, I do have an error here. This is a multiply, not an equals. Alright, if we want to find the minus b over 2m or the b over 2m, we need to rearrange. So theta over theta naught is e to the minus bt over 2m. Natural log of both sides is what we'll need to use to get rid of the exponentiation, the e to the power. minus bt over 2m. So minus the natural log of theta over theta naught is bt over 2m. b over 2m would be minus the natural log theta over theta naught divided by t. Okay, so at this point, negative natural log of 5.5 over 15, all divided by 1,000. Okay, while we're here, I do want to point out that b over 2m must have units of 1 over second, because e to the power bt over 2m, that's got to have no units, otherwise we don't know how to exponentiate that. So the interior of it is unitless. So here we're going to get units of inverse seconds as we might expect. Alright, technically you can take the minus sign inside the natural log and invert it. I'm going to go ahead and do that in my calculator to make this a bit faster, provided I don't typo what I'm putting into it. Alright. And it looks like we get b over 2m is equal to 1 point, I think that's a 0 times 10 to the minus 3 inverse seconds. And yep, 1.00. Alright. Again, there aren't a huge number of problems that relate to this section in the textbook. You may see something like it, but they tend to be plug-and-play problems. You look at the formula, you apply the formula, and the formula for damped harmonic oscillators is on the formula sheet. Okay. Next up will be forced oscillations.